At first, there was a limitlessly thick mass of issue. This mass went through an blast that led to the development of atoms, stars, and universes that we can notice today. For many years, this has been the clarification presented by physicists. However, later research has presented a new viewpoint that recommends the universe doesn't have as early a beginning as originally accepted. Rather, it could be part of a recurrent cycle in which the universe goes through a progression of cycles of development and constriction, possibly in a boundless circle. Brian Cox, a famous physicist, feels somewhat skeptical about the theory of prehistoric cosmic detonation, arguing that something can't emerge from nothing. This scrutinizing adds an interesting component to the conversation. Moreover, research from the James Webb Telescope has revealed data that goes against the possibility that the Big Bang denoted the absolute start of the universe. This leads to the critical question: if the Big Bang was not the start of the universe, then what was? Join us on this journey to the origins of the universe, where we will investigate the frontiers of the Big Bang further and answer this question and more. Assuming you are keen on keeping up to date with news about the universe and its environments, subscribe to our channel, hit the like button, share this video to reach more people, and turn on the notification chime. Scientists have fostered a detailed understanding of the universe in its earliest stages, known as the theory of prehistoric cosmic detonation. According to this model, the universe was much smaller, hotter, and denser than it is today. Roughly 13.8 billion years ago, during that period, all the components that make up our reality were formed in minutes. In this theory, our universe, including stars and galaxies, was once as small as a peach and had a very high temperature of over a quadrillion degrees. Interestingly, this stunning account aligns consistently with all current observations. Cosmologists have researched everything from the remnants of electromagnetic radiation of the early universe to the abundance of the lightest elements and have found that everything agrees with the predictions of the Big Bang to the best of our knowledge. This description fits the reality of our universe perfectly. However, despite its apparent vigor, we know that the theory of the universe's origin isn't the complete picture. There's a missing part of this puzzle, and that part is an understanding of the first moments of the universe. This challenge is due in large part to the limitations of the physical theories we currently use. The combination of general relativity and high-energy particle physics gives us a valuable theoretical framework. However, as we delve deeper into the initial moments of the universe, the mathematical complexity increases significantly, reaching a point where our current methods cannot provide meaningful solutions. One sign of this difficulty is the existence of a singularity, a point of infinite density at the beginning of the Big Bang. This concept suggests literally that the universe was once compressed into an infinitely small and dense state, which seems paradoxical. To address this challenge, we need to explore new frontiers in physics, develop an approach that overcomes these limitations, and provides a more comprehensive understanding of the first instance of the universe. Our current tools and theoretical frameworks are not robust enough to address this challenge, so we need to develop new physics that can encompass and decipher gravity and the other fundamental forces at extreme high energies. This is precisely where string theory comes into the picture. This theory aims to be a physical model capable of unifying gravity with the other major forces, especially at ultra-high energies. Essentially, string theory posits that it can provide an explanation for the first moments of the universe. Within string theory emerges the concept of an ekpyrotic universe, which takes its name from the Greek word meaning design or generation. This idea suggests that the Big Bang as we know it was the result of a prior event, implying that it was not necessarily the beginning but perhaps part of an ongoing process. Expanding the idea of an ekpyrotic universe has led to the development of a related theory called cyclic cosmology. Although the idea of a cyclic universe has been contemplated for centuries, string theory provides a solid mathematical basis for this conception. In the structure of cyclic cosmology, the universe functions as if it endlessly oscillates between big bangs and contractions in an infinite cycle that extends infinitely into the past and future. This theory of cyclic cosmology was proposed by the renowned physicist Roger Penrose, who was awarded the Nobel Prize. Penrose was intrigued by a notable mathematical relationship between the early universe, described by extreme density, intensity, and teeniness during the Big Bang, and the future state of the universe, which is described as extremely cold, expanded, and devoid of any matter. The theory suggests that these two states become nearly mathematically identical when pushed to the extreme limits. Although it may seem paradoxical, the total absence of matter could be the driving force behind the creation of all the matter we see in the universe. According to this perspective, the Big Bang emerges from what remains almost indistinguishably after all the matter in the universe has been consumed by black holes that eventually evaporate into dispersed photons in a vast void. The universe emerges from what, from another perspective, essentially equates to nothingness. However, this nothingness is still a form of something that constitutes a physical universe, an empty one. The mystery lies in how the same state can be interpreted as both a cold void universe and a dense universe, depending on the perspective. The key to this understanding lies in a complex mathematical process called the conformal transformation, which is a mathematical transformation that changes the scale of an object while preserving its shape. Roger Penrose demonstrated that the cold void state and the hot dense state can be connected through the scale change, adjusting their spatiotemporal patterns despite their differences in size. However, Penrose argues that the concept of time loses its relevance under these extreme states of being. In cyclic cosmology, the sequence of events evolves from an ancient cold state to a youthful hot state. The existence of the hot and dense state is the result of the previous cold and void state. However, this causal relationship does not follow the usual chronological pattern. As in these extreme states, both size and time lose their ordinary meanings. The cold void state and the hot dense state exist on separate timelines, which means that from the perspective of an observer within its own timeline, the cold empty state would go on indefinitely. Physics and philosophy are intertwined in this realm of cyclic cosmology. It provides speculative and detailed explanations for the origin of these cycles. However, even if Penrose's ideas gain support in cosmological advances, a deeper philosophical question still remains about the origin of physical reality itself. How did these cycles come into existence? This leads us to contemplate the justification for the existence of something other than nothing, which is one of the fundamental philosophical questions. For our purposes of discussion, we will focus on explanations within the realm of physics. There are three possible scenarios to consider in exploring the origins of these cycles. First, there might be not a truly clear reason at all. Second, there could be an infinite series of cycles where each cycle represents a different universe, and the initial quantum state of each universe is somehow determined by some aspect of the universe that preceded it. Finally, there is the option of a single cycle in a repeating universe, where the beginning of the cycle is figured out by some element of its own end. These possibilities are attractive because they avoid the need for uncaused events and provide a more intricate explanation within the physical framework. In the domain of physics, Penrose suggests the idea of an endless sequence of cycles influenced by his understanding of quantum mechanics. In quantum mechanics, a physical system exists in multiple states simultaneously until it is observed. Then, it randomly collapses into a single state. Penrose proposes that each cycle is influenced by random quantum events that give rise to variations between cycles. This concept opens up promising possibilities for experimental physicists, as it suggests the possibility of detecting subtle traces or anomalies in the cosmic microwave background radiation. The quest to understand the origins and nature of the universe has been a fundamental pursuit of human curiosity and scientific inquiry for centuries. From ancient philosophical theories to modern cosmological theories, mankind has always sought to unravel the mysteries of existence itself. In the context of contemporary astronomy and cosmology, the study of cosmic origins has led to significant discoveries and intriguing theoretical frameworks that challenge our fundamental understanding of time, space, and matter. One of the breakthrough questions that have fascinated physicists and cosmologists alike is the nature of the universe before the Big Bang. While the Big Bang theory has provided a compelling explanation for the evolution of the universe from a hot, dense state to its current expansive structure, it leaves open the question of what preceded this massive event, if anything. The concept of a pre-Big Bang epoch raises profound philosophical and scientific questions. I hope this helps clarify the text. Let me know if there's anything else you'd like to adjust.